Hi everyone. So we're going to start the second lecture today. Before we start, I asked if there are any questions. There was no questions, but if you have questions, make sure to use chat, please, and you send your questions. All right. In first lecture, we discussed vectors. Operations of vectors like addition, scalar multiplication. We compared vectors versus scalars, and we defined the norm of the vectors, and then we started talking about dot products. But before going into dot products, let me maybe touch some issues that lift off, maybe discuss it now, related to norm of the vectors and what you can make of it. So one of the things that we want to kind of make clear, we understand, is unit vectors. So a unit vector is a vector where its norm, which you remember we defined to be a 1 squared plus a 2 squared plus a 3 squared is equal to 1. So it is a vector that length or norm is equal to 1. So you can normalize any vector to a unit length vector. So normalize any A, which is not 0, to so the new vector I call a hat, which is defined to be A divided by norm of A, length of A. Now this A hat has the property that otherwise, by the way it is defined, it's just a scalar multiple of your original vector A. It's along A, right? So this is A, vector A. By normalizing, we get this vector A hat, so this is A. We get this vector, which is still A. Get this vector A hat. And A hat has the property that it has unit length, right? So this is the process of normalization. Okay, very good. Now, some vectors that play a special role are these unit vectors. I'm sure you have seen this notation before and you have used it, I just recall. Unit vectors I, J, and K. It's good to know the coordinates. So I is the vector 1, 0, 0. J is the vector 0, 1, 0. And K is the vector 0, 0, 1, right? So as you can see, they are related to the 3 coordinate axis, of course. If this is X, this is Y, this is Z, then I is along the x-axis, is a unit vector along the x-axis. J is along the y-axis. And K is along the z-axis or z-axis, right? So we have these 3 unit vectors along 3 axes of coordinates. The good thing about these things is that you can write then any vector in terms of linear combinations of these 3 unit vectors, right? So then any A which in coordinate notation has coordinates A1, A2, A3 can be written as A equal to A1I plus A2J plus A3K. I mean, this looks a bit even more complicated than this. So you may wonder, what's the point of introducing this kind of cumbersome notation, rather cumbersome notation, and instead of working with this? Well, there are reasons that this is also sometimes useful. This is better to use than this one. So each of them have their own point. So we have just, it's good to have two different notations, sometimes two different languages. You can communicate things maybe better in this language compared to that language. So just, we have to get used to this unit normal vectors. What else I wanted to say in this from the previous lecture? One example of normalizing vectors. It's a trivial example, really, but I'll do it anyhow. So here is example. Normalize vector A equal to -1, 1, say 2. Right? So it's a vector in 3D space, and we want to normalize it. Well, okay, so we have to first compute its norm, its length, right? Is equal to a square root of, well, 1 squared is plus 1 squared is 2, and then this is 4 is 6. So it's just square root of 6. That's length of this vector, right? And then what we do, we just divide this by its length. -1, 1, and 2. And of course, you can check, because we know it's a general fact, and it's very easy to prove this, by the way, from definitions, you can do it. That norm of A hat is also 1. So that's a simple example. That's what I wanted to do. Now, one of the things that we can still discuss using this notation is equations of spheres. Okay, a sphere is an object that you know what it is. It's the set of all points that has constant distance to a given. So let me now write down equation of a sphere in Cartesian coordinates. So this is radius R with center at say the point ABC in Cartesian coordinates. Okay. So this is your point. Now maybe this is not a very good notation. I put maybe I'll just use ABC. That's okay. So this is the center, and this is the radius, R. Sphere, by definition, is the set of all points that has constant distance to the center, right? A globe, but the boundary of the globe. Interior is not part of the sphere for us because we want to have constant radius, constant distance R. So you can maybe imagine this is going to be. Okay, so this is the center, which has coordinates ABC, and the radius is R. So a point then is on this sphere if and only if it has distance capital R to ABC, right? So the distance between X, Y, Z and ABC must be equal to R. But what does this equation mean? This you can just unpack this equation gradually. This is just x minus a, y minus b, and z minus c. Norm is equal to r. But this, we know what it is. This is just square root of x minus a squared plus y minus b squared plus z minus c squared equal to r. Now, we usually don't like square roots. If you can get rid of square roots, would be very good. So we can get rid of it because we can just square everything, right? So we can just square. So square, you get then this equation. X minus a squared plus y minus b squared plus z minus c squared equal to R2. Okay? Okay, so this is a very important equation, of course, because it just tells us for a point x, y, z here, in order to be on the boundary, on the surface of this sphere, it must satisfy this equation, right? And conversely, if it satisfies this equation, then it's on the sphere again. So that's a if and only if relation between the two, right? So let me give you one example maybe of to see how this can be done in action. So example, points x, y, z satisfy an equation so the equation that's given to me is like this: x squared minus 2x plus 1 plus z squared minus 2y plus y squared equal to 7. Right? So imagine I have given that these points x, y, z in the Cartesian space satisfies an equation like that. Now the question is this equation of a sphere or not? And if it's an equation of a sphere, what kind of a sphere is it? Is this a sphere equation? Right? So to do this question, we have to do just a little bit of work with this. Namely, we have to try to see if it is of this form or not, right? So for this, we notice that these three terms you can write as x minus 1 squared, right? So you can write this then in the following form. So I'm just writing from there. So you can just write x minus 1 squared, right? For this first three terms. And then this term is y squared minus 2y. What can we do with this y squared minus 2y term now? Can you tell me what should I do? Yes, exactly. I got the right answer, both right answers. I can add 1, subtract 1 to complete the square here. So this one and this term, I can just write y minus 1 squared. You have 1 and then you have to subtract 1 here, right? So we have accounted for these two terms. Now z squared, I don't do anything about it, just there. Now the right hand side is 7, right? Okay, so now this is x minus 1 squared plus y minus 1 squared plus z squared. Now this minus 1 goes over there, so this becomes 8. So this is exactly of the form that we discussed, right? So this is sphere with center. So the center is 1, 1, 0, and radius r is equal to square root of 8. Because if you write it as quadratic terms, then this is what it is, right? Okay, so any question about this kind of? Yeah, exactly. I got a lot of good answers. Very good. Thank you. That's about the spheres, and we'll do some more about the spheres and this sort of quadratic equations, even more general than spheres, quadratic surfaces later on in this chapter. One more kind of simple equation that we want, kind of objects or surfaces we want to discuss, are equations of straight planes that are parallel to coordinate axis, right? So this is equations of planes, just simple planes at the moment. We are not looking at general planes, just simple planes of parallel to coordinate axis. Right? So, well, let's draw the coordinate axis and then see what kind of equations we can write. First of all, let's look at x equal to 0. What kind of surface or what kind of shape this represents? What shape is this? Okay. So let's look at what x equal to 0 means. It means the set of all points where the third coordinate is 0. But there is no condition on the first two coordinates. So x and y, on the last two coordinates. Y and z can be arbitrary, but x has to be 0. So let's look at the coordinate axis. This is x, o, y, z. So x is 0, but y and z can be anything. So it means that this thing is just this plane, right? Of course, I just have drawn 1/4 of the plane. There is another quarter here, and half of the plane below the xy plane. But this is essentially zy plane, right? This is zy. Sometimes you don't even have to put a dash there, just zy plane. So zy plane, it's just plane that contains this coordinate axis y and z, and so because x is 0. Now I have written this x like capital X. Maybe I should have written like little x here. That would be better. Sorry about that. To be more consistent with my coordinate notations here. Okay, so then you can do more general. What about x equal to not 0, but maybe some constant, right? So x equal to 2, for example. What kind of shape this represents? Can you tell me? X equal to 2, for example. It's not exactly zy plane anymore, because zy plane has the property, as we discussed, that x is equal to 0, right? So, exactly. So it's really like zy plane, but shifted to the point x equal to 2. Exactly. So it's a plane that's parallel to zy plane, but it starts at 2. So it's really like parallel plane. Okay, so this one then I can just write is a plane parallel to ZY plane. But this time it's cutting the x-axis at x equal to 2. X-axis at x equal to 2. I need chalks, good chalks, let me get chalks. Okay. X equal to 2. So basically we know now how to draw these planes. X equal to constant is, if the constant is positive, is a parallel plane going in this direction, if it's negative going from in the back of the Z or Y plane, basically. That's what it is, right? Right, very good. The set of all points with x equal to 2. Yeah, exactly, that's the set of all points with x equal to 2. But I meant really to give me a kind of clue for the type of picture. So with the same understanding, you can write equations of y equal to constant and z equal to constant, right? So these are exactly similar to this. So y equal to constant so this is a plane parallel to xz plane, right? Is a plane parallel to xz plane. Cutting the y-axis at, for example, y equal to 0 or 1 or etc. Okay, so this time I can draw a picture. I don't want to draw it on the same thing because it's going to get messy. So let's draw on a different coordinate axis. X, O, Y, Z. Now this time we are saying, say, y equal to 1, for example. So this is this plane. Y equal to 0, this plane is. And if you want to have y equal to 1, you just shift it 1 unit forward, right? So this is y equal to 1. And of course, if it is y equal to -1, you go back of the coordinates. Right. So that's about it. I think we discussed now equations of spheres and planes. So we can go back to subject that I promised we're going to do this time, this lecture, the dot product. Any questions about this stuff so far we did? Well, you can always ask questions anyhow. So let me then, I can then move on to next topic, which is dot product. We have two vectors now. One, A2, A3, and B equal to B1, B2, B3. The dot product is defined. So I just write what I wrote last lecture. This is the notation A dot B equal to A1 B1. Yes, A1 B1 plus A2 B2 plus A3 B3. Notice that, as I emphasized, this dot product is not a vector anymore. So you take two vectors and you get a scalar. So it's a scalar. So there is another notation and terminology for dot product that has been, that's also in use. Can you tell me what other notation or terminology for dot product maybe you have used in physics or some other courses? Have you seen this at all? Yes, exactly. It's called a scalar product or inner product in linear algebra. So this is called scalar product. So dot product, you see in different books, it's written as a scalar product or product. Same as inner product. So all these different terminologies are used for this dot product, but we just use dot product. Notation-wise, also there is another notation that's in use. So there is alternative notation. I'm not sure if we use it in this course, but it's good to know. Sometimes, actually, most of the time in mathematics and physics, this is written as bracket A, comma B. This notation is also very much in use. It's called inner product or scalar product. Anyhow, so this, but we use just dot products, I believe, in this course. But just be aware that this is also in use. So then, as I said, so the question is, what is the meaning of this really scalar that we attach to these two vectors? So we have got this vector A and this vector B. And then we form this number. So one might ask, you might ask quite reasonably, oh, what's the geometric interpretation of the dot product? Exactly, that's what I'm going to do now. That's a good question, yes. So the question is, what is the geometric property of the dot product? Exactly, that's a very, very valid question. And related to that, you might complain that, I mean, why A1, B1? You could do so many other different things here, right? You could take 2A1, you could take A1 plus A2 plus B3. I mean, the possibilities are just infinite, right? Why, among all those infinite possibilities, so we picked this one, and this is going to play such a big role. Well, the answer is some of those other possibilities might be also interesting, and you may discover new things that way. I mean, nobody says that that's it, that's the only thing. But for this, the geometric interpretation or geometric property of this is the following. So the geometric interpretation of the dot product so this dot product is really the following thing. It's length of vector A times length of vector B times cosine of the angle between the two, right? Sine times cosine of it. So this is a fundamental relation that gives the relation between geometry, which is length of this vector, length of that vector, cosine of the angle, right? And pure algebra. So we are we have two things, geometry and algebra, they are somehow corresponding to each other through this magic relation, right? So this is the answer to the question, an excellent question that I was asked, and I was planning to answer, actually, to discuss it myself, which is, what's the geometric interpretation of the dot product? It is exactly this one. So the first question is, first of all, well, good, cool, but how do you prove this? Proof of this, I just briefly mention, I'll go into the proof maybe later on, but just briefly mention what it really entails. Uses the formula. So for triangles, which goes back actually to 2,300 years ago. So this formula is so old. It was known to Greeks and it was known to other civilizations, I'm pretty sure. So the formula is this. Exactly like that situation, but let's draw just as a triangle. So imagine this is length, has length L1, this has length L2, and this has some length L. And there is this angle theta here. So the question is, if I know L1, L2, and theta, can I know L? Do I know L? At least in one case, you know that, right? In what case, you can easily tell me what this length L is based on L1 and L2 and theta. Can you tell me in what case you can know that? Exactly, right triangle, exactly. At least if theta is 90 degrees, right? This is L1, this is L2, this is, well, they don't have to be the same even. This is L. In this case, I know that L squared is equal to L1 squared plus L2 squared, right? This is Pythagoras' theorem. Then the thing is, the beautiful fact is that you don't have to have 90-degree angles all the time. If you have any angle, you can still compute this. And this is very important in surveying and measuring the land and stuff like that. So how can we compute this? Well, the formula in general is this. L squared is equal to L1 squared plus L2 squared minus 2 L1 L2 cosine of theta. Of course, you notice if theta is 90 degrees, cosine of theta is 0, so you recover Pythagoras. So if theta is pi over 2 is 90 degrees, you get Pythagoras. But this is more involved than Pythagoras. There is an extra term here which is missing in Pythagoras exactly because the two things are orthogonal to each other, 90 degrees. So it's more general. And here we are dealing with a more general case, by the way, because this is theta. So then here, just apply this rule. Formula to the triangle. So this is this triangle, I call it star. So in this triangle, then L1 is equal to norm of A, of course. That's our definition of length of a vector. L2 is equal to norm of B. And now, so this is L1, L2. Now, what is L? What is the length L? Can you tell me what the length L is? Yeah, this was called cosine rule, exactly. So this length L, of course, you see, what is L in terms of A and B? If you take this vector, add it to this vector, you're going to get B. So L is B minus A, or A minus B length. So L is equal to length of A minus B. because this is the difference of these two vectors. This vector is the difference of these two vectors. Right? So this is what it is. Okay, so then you can put all these things into this formula, and this formula will pop out. So this formula is exactly equal to this what's it called, cosine rule or whatever, I think, from Euclidean geometry. So this is a very, very important formula, as you notice. One of the things that I should say, maybe I should have said before this, is that length, what is the relation between length and dot product? Maybe this is something we have to know already. We have to know this relation between norm of A and the dot product. Well, norm of A squared is equal to A dot A. This is a very important formula, right? And its proof is absolutely easy because left-hand side, proof of this, left-hand side is A1 squared plus A2 squared plus A3 squared. But right-hand side is also A1 squared, A2 squared, A3 squared, right? All right, so you see that the two sides are equal. So in the proof, we have to use this observation also for the proof of this cosine law. Now, what are the applications? Any question about this proof and the cosine law and these things so far? Okay, seems there is no question. Okay, so one application of this thing is that we can tell exactly when two vectors are orthogonal to each other. And that's a very important fact, very valuable observation. So that's orthogonality. So let me write it here. So this is, call this star then. So a corollary to a star so vectors A and B are orthogonal to each other. If and only if. When I write IFF, it means if and only if. It means it's implied and it implies both directions holds. Right? If and only if A dot B is equal to 0. So in other words, so notation is this. I'm not sure this is a notation that's used in book, but sometimes I use A is orthogonal to B if and only if A dot B is equal to 0, if and only if, of course, by definition, theta, angle between the two is pi right. And this is angle pi right. So that's the orthogonality. Okay? So, but in general, vectors don't have to be orthogonal to each other. They can have some angle, like theta. And the good thing about the formula is that we can measure the angle from the inner product in general. So in general, then, the angle, so I would say the unique, I will explain what I mean. The unique angle, theta, between pi and 0, between A and B, can be obtained from a star. So if you just solve this equation for cosine of theta, then you get cosine of theta equal to, of course, you get cosine of theta equal to, so cosine of theta is equal to A dot B divided by length of A times length of B. Okay? So you can write this equation in a different way. You can just say theta is equal to arc cosine of A dot B divided by norm of A, norm of B, right? So when I say the unique angle, I just mean this. Given any two vectors, A, B, so they can have zero angle, and then you move. They can have pi over 2. Then you move again. Then you can have again pi here, pi. But then you move in this direction. Okay, in this case, we are not going to measure this. We are going to measure this, because this is the angle which is between 0 and pi, between A and B. So it's a little bit of ambiguity here, but by taking care of writing theta between 0 and pi, we have tried to destroy the ambiguity. We're just saying that there's a unique number. There's nothing ambiguous or not well defined about this. There is a unique number between 0 and pi, unique angle, that satisfies this equation. And that's the geometric meaning of these different things. So it's always between 0 and pi that we can use this formula in measure. So, yes. Now, one of the things that we want to use this formula for is the projection. So let me just, so that's a very important actually concept. It's called projection formula. So what is projection formula? So we have got a vector B. So this B is a non-zero vector. And then if you have any vector A in space, you can drop a perpendicular line to B. I mean, this kind of stands to reason that you can imagine that there exists a vector here along B, which is obtained by drawing, by dropping a orthogonal kind of line from A to this line B. In other words, there is a point on this line B such that we will see later on that the distance between this point and this point A is minimal. And that point is exactly, we will see that is going to be exactly, anyhow, so the property of this line is that this is exactly 90 degrees. If any other line you drop, this line won't be 90 degrees. So this vector has a name. It's called the projection of A along B. So projection of A along or onto B. So it's denoted by this. It's this notation. But the question is, oh, what is it? Can you give me a formula in terms of vectors A and B, right? Can you give me a formula in terms of A and B, for example? So this is equal to what? To answer this question, the only thing that we have to know is to know the length of this vector, right? So, so first, what is length of this vector? Because if you can compute the length of this vector, then you can multiply by unit vector in this direction, and then we'll see how it goes. Then that's going to be easy. But the question is, what is this length? But here, for the length, there is a famous consequence of this relation, which is the following. Imagine, this is, you have used many, many times in physics, for example, I'm sure, maybe high school either. So the question is this. If you have an angle like theta, and you drop this line, what is this length? In terms of this length. Imagine length, this can be just triangles. Imagine you have this triangle L1 and this triangle, you project it here. What is this length in terms of this length? Can you tell me?
L1 cos theta?
Exactly, exactly. Absolutely nice. Very good. So L is equal to L1 cos theta. That's the formula that you have all seen, I'm sure. Many others also. Okay. So if you use this formula in this picture, then this is L, right? And this is L1. Okay, so length of this then is equal to L1, which is length of A, just norm of A, times cosine of the angle, right? But cosine of theta we know already in terms of dot product, so let's continue. Is equal to norm of A times A dot B from the formula above, A dot B, divided by norm of A, norm of B, right? So there is one simplification. So you get, so far we have got length of this vector is equal to A dot B divided by norm of B, right? Now the question is, what is the vector itself? Now we know its length, but what's the vector itself? But the vector itself is just unit vector times. So it follows that the derivative proj AB is equal to a unit vector in this direction, B hat, times its length. So this is A dot B divided by norm of B times B hat. But we already know what B hat is, right? So that's equal to B divided by norm of B, right? This is the B divided by norm of B. So this is A dot B times norm of B, or length of B, times B divided by norm of B. So the final formula that we get, which is very important, I'm afraid you have to memorize it. So this is equal to A dot B over norm of B squared times B. So this is the formula. Okay, so that's the formula. You can kind of have a rough check that you have not gone too far, meaning in kind of in the wrong direction, by noticing that this is at least a vector in the direction of vector B, and we wanted to have a vector in the direction of vector B. Of course, this is not the proof. It just means that the direction of this vector is exactly along B, but the length is the important thing, and the length was computed by this formula that was actually mentioned from class, that this is L is equal to L1 cosine. So I think we are done for today. So I'm going to stop the video, but I will be here. If you have questions, you can ask your questions off camera, and then we'll discuss. Thank you very much, guys. Have a great day. I'm here still. If you have questions, Feel free to ask questions. Thank you all.
Hi, Professor.
Hi.
Yeah, do we need a calculator for this course?
No, you don't need a calculator for this course, right? And actually, during exam, calculators are not welcome. But it's useful to use calculators. I mean, just for your understanding and maybe doing calculations, even doing symbolic calculations, graphing, stuff like that. This is kind of very useful as an aid to your intuition. But for the course, definitely, no, you don't. I mean, in other words, there will be no question that it's based on calculators. Yeah, there was one question that was about wondering what sections we have covered today. Yeah, this I have to say, I have to give you the sections also. So this I will write down I will post the answer to that question later, because I don't memorize sections, unfortunately. Oh, on the last line, would it be wrong to have AB squared in the numerator? In the denominator, you mean? Oh, AB squared. Oh, no, I think it depends what you mean by B squared. I mean, this is the formula. I mean, we don't have something like B squared. This notation we haven't defined, if that's what you meant. You know what I mean? So I think that's the formula. It should be the way it is. Okay, great. Very good. I meant to ask who is following this course from campus or from London or from out of London, but then I'll ask later on, so that's okay. Anyone among you following from out of Canada, for example? Oh, it's not a very large population anyhow. We have 9 participants left, so. Okay, it looks like there are no other questions. Then I will end the session and then I will post the video. Okay, guys, have a great weekend. Bye-bye.